we have organized today is sort of a mini symposium where our students will talk about their works, etc., what they have been doing, at least a few of them. And we'll have Muthu, so it's going to be an interactive session, and I want you guys to make the illustrations. He's already done, but still try to make the talks as much pedagogic and create some opportunities to discuss so that we can take it through. Okay, so first talk is by Hitesh. So Hitesh, we are starting at 11:02. So the talk slot is essentially 20 minutes, but what I will do is I will stop at exactly at 15 minutes or 16 minutes or so, and let us discuss for another 2-3 minutes, and that's it. Okay.
So we should interrupt in between
slide numbers, etc. I will need to stop.
Yeah, we should be asking at the end, or can interrupt in between.
I think we can just ask at the end. Okay, so we'll just let these guys speak for 15 minutes, and then we can have like 4 to 5 minutes. Yeah. Okay, Krish, all yours. Please start.
Hi. So first of all, thank you, organizer, for organizing this beautiful symposium. And also, I would like to thank Professor Muthu Kumar for visiting us and giving some nice, beautiful lectures. So today, I am going to present one of my work, Coil to Global Transition via Solvent-Co-Solvent Attraction. This work I carried out with my supervisor, Professor Satyavani, and one of our collaborators in IIT Delhi, Divya Nair. So I'll explain the term coil to globule. So coil is basically an extended kind of structure of a polymer. If a polymer has an extended kind of structure, in literature we call it a coil kind of structure, and globule is a collapsed kind of structure of a polymer. So these are just a nomenclature. So this is basically extended to collapse transition of a polymer, of a single polymer we have taken. So in the mixture of solvent and co-solvent, so the solution contains a single polymer and solvent and co-solvent, and in that we are looking at this coil to globule transition. So before that, I just want to tell what are the polymer conformations in different solvent conditions. So in the general notion, we call something called good solvent condition when polymer adapt an extended like of structure, and in general, like monomer attraction in that case will be lesser than monomer solvent attraction, and it will have extended kind of structure. And then we will have a poor solvent condition where the monomer attraction is greater than monomer solvent attraction, and polymer likes to be in this globular form or collapse form. And then we can also have a theta solvent condition where this monomer attraction is similar to the monomer solvent attraction, and this polymer will adapt an ideal kind of or Gaussian like chain structure. So how this radius of gyration, that radius of gyration is basically extent of the polymer or end-to-end distance, goes with the number of monomer n or molar mass is 3/5 for the n to about 3/5 for the good solvent condition, and for poor solvent condition it goes as 1/3, and for ideal kind of thing it goes as 1/2 random walk statistics. So basically this can be derived from the free energies of the system, and in general this r power n goes as n power nu, where nu is we can say as a scaling exponent, which we can use to find whether polymer is in the distinguish whether polymer is in the good solvent, theta solvent, or poor solvent condition. So why this coil to globule transition? Just a short this thing. So as I mentioned, the coil to globule transition is basically representing a change in the conformation of the polymer chain from an extended coil-like structure to a very compact globular structure. So basically, this coil to globule transition is a kind of phase transition, you can also say, which is observed in these polymers. So this understanding of these thermodynamics and kinetics of this transition contribute to our knowledge of the phase behavior of the polymer system. So, and in biological system also, we can say this coil to globule transition is relevant to the like folding and unfolding of the biopolymer, such as protein and the nucleic acid. Also, it can help us in understanding this LLPS, liquid phase separation kind of stuff. So this is why we are studying this coil to globule transition. So there are a bunch of ways through which we can achieve this coil to globule transition. So I'm mentioning a few of them. So one of the way could be like changing the solvent condition from good solvent to poor solvent. It will go from extended to collapse. Also, one of the study we have done earlier is in the presence of attractive Crowders. So if a polymer is in presence of attractive Crowders only. Crowder, I am using a very generic term which can be anything other than polymers. And if there is attraction between the Crowder and the monomer, polymer will adopt an extended kind of structure in order to maximize the surface of the polymer. But as the attraction is increased furthermore, after a threshold value of that, polymer will form a global kind of structure, because these crowd are now acting as a bridge between the distant part of a monomer and inducing this collapse form. And in the charged polymer also, if we have a charges on each monomer in the presence of counter ions at lesser value of charge density, we have an extended kind of structure. But as we increase A is here charge density on the backbone. As we increase A, we see again a collapse kind of structure, extended to collapse in the charged polymer system. Also, we can achieve this coil to global transition through the temperature change. So we can change the temperature. It will go from extended to coil or coil to extended, given whether it will depend on whether the solution contains LCST or UCST. So lower critical solution temperature or upper critical solution temperature. So they will have a coexistence phase where there will be above a temperature will be homogeneous phase, and below that temperature could be two phases. So, and then today, like I'll just go through a little this way. So this in literature known as something called co-known solvency. So what is co-known solvency? So co-known solvency is a phenomena where a polymer that is soluble in two different solvents individually becomes insoluble when these two solvents are mixed in a certain proportions. What it means, so suppose we have a solvent and a polymer, and you put polymer in that solvent, it will be miscible. It will be miscible. That means it's a good solvent, or it will extend. And in the solvent B also, it will be in the miscible form, and the chain will have a conformation of extension. But if we mix these two, solvent and co-solvent, in a certain proportion, and then we put the polymer in it, it will form a globular form. So it's kind of two good solvent are effectively giving rise to poor solvent condition. And for the test example, people study this example a lot to understand the mechanism. So this polymer PNIPM is soluble in water as well as in alcohol. But if we mix alcohol and water in a certain proportion, it will precipitate. The alcohol will, this polymer will precipitate and form a global kind of structure. So this is what co-known solvency is. So people are trying to understand what is the mechanism for this. So there are like various bunch of reasons for that. So like some of them I'm mentioning here was very chemistry specific. They are like they will have a preferential solvation where water and methanol compete to solvate the PNM. And or it could be disruption of the hydrogen bonding, where already like water have a strong hydrogen bonding with the polymer, but in the presence of methanol, there could be disruption of this hydrogen bonding, and dehydration can induce this collapse form. Or there could be an entropic effect as well, where the rearrangement of solvent molecule in the presence of co-solvent can give rise to this collapse behavior. So what we are trying also, so people are now trying to get a very generic model where they can explain this mechanism, which do not contain any chemistry information. So earlier the reasons I mentioned was mostly like chemistry specific, but here what people have tried is they try to build a model which is very generic, which do not have any chemistry details in it, and try to find what is the universal mechanism that is being followed by this phenomena. So one of the earlier paper I am mentioning here is saying that polymer collapse is miscible in good solvent is a generic phenomena which is driven by the preferential adsorption. So they concluded that this phenomena of co-known solvency is derived by this preferential adsorption. That means solvent or co-solvent will adsorb on the surface of the polymer and will give rise to the collapse behavior. But sometime later, this new paper does also ask the same question: does preferential adsorption drive co-known solvency? And the answer they found was no. So this preferential adsorption is neither a sufficient condition or nor necessary condition. You can have adsorption, still you do not see any co-known solvency, or there can be without adsorption there can be also this collapse behavior or co-known solvency. So the point is there is no universal mechanism that has been found which can give us the better view of this. So in that direction we are also trying to develop a very minimal generic coarse grain model that shows this co-known solvency behavior, or you can say this coil to global transition, and we are just trying to be very generic in that sense. So the rest of the talk I'll be giving from this reference. We have this archive version of this. So what our model is very general phenomenological model, coarse grain model, where we do not have any chemistry specific interactions. We just have a very single polymer, and then which is submerged in a solution of solvent and co-solvent. Solvents are blue and co-solvents are the green, for example. And the polymer chain is connected to each other. Monomers are connected to each other by the harmonic bond, and other interactions, other particles are interacted by this van der Waals interaction given by this Lj potential. So this R less than R, this RC will give us whether the interaction is attractive or repulsive. If we take RC to be 1.12 in general, we call it a WCA interaction, that is weak Chandler-Anderson interaction, that is just repulsive kind of interaction. If we take like 2.5 or 3, we see a attractive interaction with the particle. So in our model, these are the interaction parameters we have considered. So all of them are WCA except the last one, which is solvent-co-solvent. So we have a mixture of solvent, co-solvent and a polymer, and other interaction are just WCA, just randomly going gas, and then we have a attraction with the solvent and co-solvent. So this is the only thing we have taken, very minimal interaction in that sense. So these are some of the results. So what we noticed, if had there been this value also 1.12, that means WCA, we would have seen a straight line. I have not put here, but yeah, you can take my word. So this value will be straight line if we have this as also WCA. As we put this attraction between monomer, solvent and the co-solvent, we see. So I'm plotting here on the x-axis is fraction of the co-solvent. So what I'm doing here is increasing the fraction of the co-solvent in the solution, and then I'm measuring on the y-axis radius of gyration of the polymer. So we see when there is no co-solvent, x is 0, we see polymer has value around 9 to 10. That means the more in the extended state. You can also see this extended state from this inset also, that alpha I'm plotting is asphericity, which gives us the asymmetry in the system. Value 0 of the alpha means it's symmetric, that means it's a spherical object, and non-zero is more extended in one direction. So you can see when the x is 0, that is more extended kind of structure, and as we increase xc, we see a nice coil to globule transition with the xc. And this is again going back again to the one because of the symmetric case of the solvent and co-solvent. There is no specific interaction with solvent or co-solvent, so it's going again to the same point. Also, we are trying to see the arrangement of the particles, whether solvent, co-solvent, how that goes with the xc, and we see there is also non-monotonic decrease after this value, where as at the xc equal to 0.5, that means equal fraction of the two solvent and co-solvent, we see a most globular form. You can also see here, and in this case also. So to understand it analytically a little, what we did, we invoked Flory-Higgins theory, very basic Flory-Higgins theory, where it has two terms. One is combinatorial term, meaning combinatorial term, which is giving us the entropy of the mixing, and this second term is energetic part of the interaction. So total free energy will be the sum of the two, and as we plot this with the function of phi c over phi s, that means the fraction of the two, ratio of the fraction of the two, we see a nice minima at phi c over phi s equal to 1, equal fraction. But we also notice that the major part is coming from the energetic part Fv compared to the entropical part. Also, when we plot it with the radius of gyration we got in our simulations with the function of phi c over phi s, we see again the trend is kind of same, and also the minima of that is coming at phi c equal to phi s. That means equal proportion of the two because of the symmetricity. Then we also look at the effect of the temperature, where we saw that as we increase the temperature, this effect is fading away. That this, as you can see, this one is not showing this very nice coil to globule transition. And this, as we plot this also with the different temperature, we see this energetic pulse is also reducing and showing the same trend as radius of gyration for this. So from this we are arguing that this phenomena here in this case, with the solvent co-solvent attraction, is governed by the energetic part of the free energy, and it also follows the same trend at radius of gyration. So this is summary of what I have told here. So the main point is the attraction between solvent and co-solvent seems to be sufficient in induce this collapse of a polymer chain in a mixture of two good solvents, and this the polymer is fully compact when the fraction of the solvent and co-solvents are equal, and also that can be explained by Flory-Higgins theory. The energetic part of Flory-Higgins theory follows the same trend as polymer's radius of gyration, and also with the temperature we see this effect is fading away. Still there are future direction to it. I mean, this work is still, we can do very much more to that. So this is, as I said, is very minimalistic in the model. So we can have, we are not taking any chemical specificity, But since this is this phenomenon is very chemical specific, not all the polymer and all the solution will show this kind of behavior. We have to have taken take some of the chemical nature of the system, which we will do. And also what people are also trying is to find a universal parameter which we can tune to get to find the parameter which can govern this phenomena. It can be set of combination of some of the part. So I'm mentioning a very recent paper. This group has mentioned that this parameter chi ps minus chi pc plus chi sc, where chi ps you can think about in the sense of interactions. So chi pc meaning interaction between polymer and solvent, negative of that means attraction between them, and positive means repulsion between them. They said that this universal parameter can act as a universal parameter which can govern this. So they mentioned two regimes. They said that when this value is less than 0, we will see this cone on solvency effect, or also if the value is greater than 2, we also see. So in our case, this value ps minus pc is same because we are not taking any specific interaction with the polymer solvent and polymer co-solvent. It goes 0, at chi c is negative in our case. So this also matching with our simulation result. When the chi s is negative only, it will show this cone on solvency behavior. But still it will not complete the story, so still working on some of the work. With this, I would like to thank.
Thanks, Venkatesh, for putting in time. Questions? Let's have.
One question I have. See, when you are simulating your problem, you are taking this Reynolds zone potential, which is a long way.
Is it short?
1 by r, how it is getting shorter?
Not 1 by r. So
No.
this
When r going, say, this potential you have.
R power 12, R power 6.
R power 12. Why are you calling a shorthand?
It goes below this 1 by r.
Exist all over there.
No, but we shift this potential to 0 at certain value as this RC you can mention. So RC will
Then you have this harmonic.
that is between the monomes.
When you are simulating this problem, this is like a ab initio. And what you are saying that what you find in the Flory theory, right?
No, this is classical, not ab initio.
Huh?
This is classical MD.
What do you mean by ab initio?
We have quantum effect in there.
No. And you are simulating your second order differential equation in the presence of this potential. This classical ab initio problem.
Yeah, so classical.
Only you are changing the parameter, which you are not taking chemistry, you are taking
This
second
epsilon,
order.
yeah.
So this is you are solving this problem. Suddenly you go to the Flory-Huggins, which is a mean field theory. And both are same. So what is the why? This is not a mean field theory. What you are doing.
Yeah, this is a simulation. I mean, we are.
No, don't use the word simulation. This is not a mean field theory. You can do whatever way, simulations or anything. This is not a mean field theory. Flory-Huggins is a mean field theory. You are finding that observations are said. Why? And what is the connection between mean field theory and this?
So the
Why
density.
should we do this when everything is a mean field theory is given?
No, the density we consider here is quite large compared to it can be in the middle field regime.
No. First, understand the question. This is not a mean field theory.
Yes.
When we say not a mean field theory, means you are taking into account whatever in your problem, all sort of a fluctuation. Right? With Flory-Huggins there, whatever I learned from last 3 lectures, some sort of fluctuations you are not taking into account. Right?
Yeah.
And your result is matching without fluctuations, right? With whatever you are taking into solving with fluctuations. It means that in your problem, fluctuation is not important.
Yeah. So the answer, I think the reason to that is why this is working. You are asking. Could be the density we are taking is very high. So where this mean field will arrive.
Yeah, so you had shown that at the value of xc is equal to half. So xc was the ratio of this co-solvent and solvent.
No, only fraction of the. Yeah.
Yeah, right.
F.
Fraction of the density. Right?
Yeah.
So are there any specific reason that when you mix them by only by this equal amount, then you get this Rg to be the lowest value, I mean, then the polymer is like not.
What's the physical intuition you're asking?
Yeah, like it can be somewhere else apart from x is equal to half also. What is the symmetry that is driving?
Symmetry of the interactions. So there is no specific interaction with the polymer to solvent or polymer to co-solvent. For the polymer, solvent and co-solvent are the same, right? They are not seeing, the polymer is not seeing solvent differently or co-solvent differently. So that could be a symmetry case. So if we take preferential attraction, that means solvent is more attracted towards co-solvent of that sort, then we will have this value minima will be on shifting on the left side. That also we have done. So if we take a preferential attraction, suppose solvent is more attractive towards the polymer, then this will not be at xc by x. This fraction will not be 1. The ratio will not be 1. That will be lesser than 0.5.
Going back to the earlier question, you simulate how many chains? You simulate only single chain. Right?
Single chain.
One chain, single chain. So it's not in the configuration. Right. So how do you implement the flow rehabilitation theory which is involved? How do you implement in your comparison? I think that's the question.
That's the question.
That's the question. You said with the mean field theory highly concentrated, but you don't have that in your simulation. You have only one chain. So how do you, please go back, if you don't mind, go back to the flow rate theory. That is the question. And see, when you write if combinatorics and interactions, this is a lattice model, right? And then when you compare the simulated this curve, so too good to be true, I think that's the question. Too good to be true. So how do you take this bulk free energy to a single chain? That's the question. I know the answer, but I want you to.
Okay. So, like one of the things we are taking is the periodic boundary condition. We are simulating like bulk of that, not boundary effects. The other reason I could say is that chain is single, but there are solvent and co-solvent which are high in number. Like we have taken the density to be 0.9, the volume fraction, the volume fraction of that.
Sorry, we don't want to take too much time. Go back to the previous slide. Yeah, go back to the calculus. So that one, how do you carve out the volume of that object, that fluctuating object? That's the question, right? When you do the simulation, that's what you get normally, right?
Fluctuation in the polymer.
Yeah, in the confirmation. So what do you give volume for your flow theory? So, okay, we can take this.
Yeah, the connection is missing. I think I think everybody is asking.
Yeah, the mean field.
Huggins theory essentially gives you the answer for the non-covalence index. Then what is the point of doing this? There is a connection somewhat missing, or maybe it's there. So we just discuss.
But I can answer in that sense. Like the density we are taking over is in the enough regime that we can take the concentrated and connect.
So yeah, so I think discuss with other people, etc., just to set up and then Rahul go next. So okay, let's thank Nitish for dynamics in ring polymers.
Good morning everyone. Today I will talk my work done in collaboration with Professor Pinaki Chaudhary and Professor Satyavani Varamkarla. So we are mainly interested in characterizing the glassy dynamics of 2D ring polymers. So first of all I will start with the introduction of the subject. So what are glasses? Glasses are disordered materials that are in frozen, jammed or arrested states. So here I have a picture of normal silica glass. In the left hand side you have this amorphous structure, and in the right hand side you have a crystalline quartz structure. So the operational definition of a glass transition is like when the viscosity of a liquid exceeds this 10 to the power 12 Poiseuille, Pascal per second, or the structural relaxation time exceeds 100 second, we call that temperature as the glass transition temperature. And here we have the famous Angel's plot, where we have they have plotted the relaxation time scale with the inverse temperature. And as you can see in the plot that with 2 to 3 orders of decrease in temperature, there is an exponential increase in the relaxation time scale of the dynamics, which is not very well understood till today. So the next question is how one creates a glass. So the most common method of creating a glass is by quenching a liquid. So typically when you cool a liquid, you get a crystalline structure, but if the cooling rate is fast enough that you avoid this crystallization process, you get this glass which is a disordered solid. So here there are many open questions like when does one avoid crystallization, what are the, so glass also has this property called as dynamic heterogeneity, where near the glass transition temperature the regions in the system have different dynamics, like some particles are fast, some particles are slow, and there is also many other things to characterize, like as the aging dynamics, or is this a true phase transition. So also glassiness and the physics of arrested states of these disordered structures are relevant for wide range of applications. In the first snapshot in the A panel we have colloidal system, where we see this disordered arrangements of colloids. In the B panel we have living tissue, and in many of the living tissues also we see this glassy dynamics. And on the C panel we have a colony of ants, where they are like arranged in a disordered fashion. So the point is, like, glass is ubiquitous, and it can properties can be extended to a variety of systems. So the main question we are trying to ask in our work is, like, how does particle shape influence the glassy properties of the material. So in the literature we have various studies where the people use this WCA potential or point particles as the model system, but there they lack this degree of freedom where the particle can change their shape. But in various biological models, the shape change is also a very important factor. So to characterize and to understand this how this shape changes influence the glassy properties, we introduce we use this ring polymer model, where the interaction between the monomers is modeled via the WCA potential, which takes care of the excluded volume interaction. And to bond two monomers we use this Finney potential, which is like a spring potential, but it is like it diverges much more faster near the cutoff, the bond cutoff value. And to model the stiffness between the two bonds, we use this V theta potential, where here k theta is the value which parameterizes how stiff the two bonds will be, and pi is the equilibrium angle between the two bonds. So now the first system we study is the monodisperse system. So here each ring consists of 100 monomers, and the stiffness of the rings is also fixed at k theta equal to 100 value. And then we increase the density of the system, and the first thing we characterize or we plot is the mean square displacement. And as you increase the density of the system, the mean square displacement goes down, and first it shows a ballistic motion, and then if the density is very low, you have this diffusion. And if the density, when you keep on increasing the density, then there is this emergence of plateau, and depending on the density, if the density is very high, the system shows subdiffusive behavior, and if the density is low, the system is diffusive. The interesting thing is, if you extract the diffusion coefficient from this MSD plot, you get this non-monotonic behavior in the dynamics. So what we see is that at density 0.10 there is a sharp decrease in the diffusion coefficient, and when you again increase the density, it goes up, and there is again another sharp decrease in the diffusion coefficient at density 0.20. So to understand these things, we now go to the structural properties and try to see what is causing this slowdown. So the first plot, in the first plot we have the pair correlation. Here we see that at density 0.10 there is a emergence of long range order, and if we plot a 2D pair correlation, we see that at this density, at density 0.10, the rings arrange themselves in this hexagonal order, and because of which this emergence of 2D order, the system slows down. And but if you increase the density again, the rings are deformable. So from the spherical shape, they compress, and so the sparsity increases, and now the system can no longer sustain this 2D order, and thus the dynamics increase. So this is on the far left, we have the sparsity versus density plot, which shows a sharp increase at this density 0.10. So for this second decrease in the diffusion coefficient, we plot first, we see this snapshots at this three different densities at 0.10, 0.20 and 0.22, and this sharp decrease was at density 0.20, and here we see that the rings arrange themselves in this 1D stacking. They there is this emergence of this 1D order, and because of which the system slows down. And to quantify this, we plot this local orientational order parameter, where the theta j is the delta theta j is the angle between the largest eigenvector of the two neighboring rings. So again here at this density 0.20, we see this sharp peak, which corresponds to this 1D order, and then if you further squish the system, this 1D order is lost, and the system form domains, and because of this disorder it again speeds up. Now then, next system, we wanted to introduce study the effect of size and stiffness polydispersity in our system. So we first chose this size polydispersed system, where we draw the number of monomers in one ring. We draw it from a uniform distribution, and the range of the distribution depends on the polydispersity percentage. So here, if you plot the dynamics for both the stiffness and size polydispersed system, the non-monotonicity in the dynamics is completely gone, because now the system is not allowed to get arranged into this 2D or 1D order, and hence this non-monotonicity in the dynamics is lost. But still, both this system size and stiffness polydispersed system, they behave differently. They behave differently in a sense that the glass transition density for these two systems is different. And to see that in what sense they are different, we plot this first on the left hand side corner, the distribution of sparsity, and for the size polydispersed system, for the very high density also, the smaller rings retain their shape, which is and the larger rings are completely flattened out. But for the stiffness polydispersed case, there is a very small narrow density range where different rings behave differently. Here, for example, at density 0.11, we have a range of shapes for stiffness polydispersed system, but if the density is less or more, you see a unimodal distribution. And similarly, if you say, look at the structure of these systems, you say for the size polydispersed system, the structure is completely lost, but for the stiffness polydispersed system, the structure is still persistent. And if you plot the local orientational order parameter, again there is non-monotonicity for the stiffness polydispersed system, but for the size polydispersed system we have a continuous trend. And this is the conclusion slide, and thank you. If you have any questions.
Thank you, Rahul. So I think we have quite some time.
Please go to the earlier one. I didn't get this. Please go back to the this one.
Yeah.
So I didn't quite get the right hand side of this picture. So that's it. So you are plotting the diffusion coefficient from density.
Yeah.
These would not be your key results. So that's why I want to understand. So how did you get your diffusion coefficient?
Just by doing this for the late times, like for the in the asymptotic limit, if the MST is linear with time, from there you extract this diffusion coefficient.
So you are extrapolating the very long time limit.
Yeah.
But if this is, when you say, let's look at 0.18, your density is 0.18,
Yeah.
your orange line.
Yeah.
That's one trajectory, or it's average of 1,000 trajectories?
Not 1,000, it's average of 50 trajectories.
I think we should do more. Because, because in every, please correct me if you did the simulation, right?
Yeah.
Beautiful simulation, I remember the right? So the crossover from your sub-diffusive region to the asymptotic region is a very highly variable.
Yeah.
Right? Because every trajectory is going to see what the neighbors are doing, that's going to be different. So particularly for these systems, you need to really average over really thousands of trajectories.
Yeah, the simulations are very expensive. Like
yes, indeed, because it's a very complex system. Because you are making a very profound comment about non-monotonicity.
Yeah.
So that's your key result.
Yeah.
So your reviewers will come and haunt you. They'll ask you what the error what is.
Yeah.
Right? If you say 50, they'll say no, that's not enough.
Yeah.
If I were a reviewer, I'll ask that question.
Yeah.
So please, I think you need to pay attention to this because it's a big effect. It's a logarithmic scale. I understand that.
Yeah.
Right? But still, particularly when you go to 0.2, right? You don't even see the crossover.
Yeah, it's not. It's slowly approaching diffusion, but
so,
it's not exact process.
Right. Therefore, your number 0.225, your diffusion is going up, for example.
Yeah.
That's not reliable. That's I won't take it. I won't believe it. Because if you went longer for that simulation, it's going to be hard. When you take the asymptotic limit, that diffusion is going to be much lower. So it's going to come down. It's not going to go up. It's going to go come down.
Yeah.
Do you agree?
Maybe, but at this density, there is this emergence of 1D order, which is also restricting the motion of the rings. So.
No, I'm just worried about the data analysis.
Yeah.
What I'm trying to say
Yeah,
is,
that I understand. Data analysis part I understand.
So here, it is not. The slope is not 1.
No, so that is so for this point at point 0.225, I have a different curve that because the plot will get too crowded. I have not plotted it. Okay.
Even I have a nice question. How are you sure that is not a numerical error at this point? This is just a one point you have, right?
Yeah.
If I want to be sure that something is coming, I have to check here and here also. This may be a numerical error. If I put here, this is a very nice curve.
No, I have checked for different pressure.
If the curves where it's very clear, then there is a non-monotonicity. I mean, the correctness of the numbers, that is what we have to fight for. That's a different problem.
No, but this
No, if you look at the
number.
curves, numbers we can worry about. But if you look at the curves, then there
No,
is
but 1 point I cannot rely. Na? Just you need a
fine,
one over
that's
left
a-
and right.
That's the point taken. But non-monotonicity there is no problem.
No,
This
the,
may be
the-
a numerical error.
no, this non-monotonicity at the first instant, that is clear because of the presence of this 2D order.
You know, in the numerical problem, there may be some fluctuation of a point. You can go deep. How am I sure that that is just using just 1 point and I am going to say
No, this-
a big claim? Maybe you are right, but I am
Yeah,
saying we
no.
have one data point.
Yeah, but it is very hard to get data points near this dip because this,
You have to
this
bring some
that is
other
not
way
an
to
argument.
justify
So maybe
it.
you should think about it. Like I think some points for both of them.
Yeah.
Some points. So think about it and then.
yeah.
Very interesting. Can I ask something?
Yeah.
Yes, then Arijit.
Yes.
After that.
Yeah.
After Arijit, then you first.
No, just a naive question. I don't see any error bars here. Some plots you have.
Yeah.
This plot, for example, when you are on the left side of the plot,
Yeah.
why can't you shade to show the variance of
Yeah.
where you are doing? So if I
Yeah,
shade it,
I'll
then
add the
then we
variance.
see
In the other
variance
plots, I
there.
have the variance as the error bars.
Yeah, here
but-
you had. So
Yeah.
the other is the case that the error bar is very small here, that on the right side that we don't see it, or it's just not shown.
It's not shown, but I will look at the error bars. Check.
A very quick question. Right? This is a very, very difficult problem. So your starting configuration will be extremely crucial. So the way, when I look at this snapshot, every ring is like a balloon is blown up.
Yeah.
Right? You don't see interdigitation, right? You don't see one loop coming in after
Yeah.
another. So I wonder, is it deliberately that's avoided in making the configuration?
No, it's a 2D system, so they cannot interprint.
No, but you can have two chains, right? You can
Yeah.
make it. I don't say anything like, I'm sorry. I would have something like, like that.
Yeah.
It's not like always like this. It doesn't have to be like this. I could
Yeah.
have, right? So I could have something like this,
Yeah.
like that. So it looks like you are very quite a semi-flexible chain.
Yeah. So the yeah.
But you don't see it, right?
No, here the because of the density and the pressure and these are at very less pressure values, so these are ballooned up. But if you look at these plots, here the rings are squished because these are at
Something like that.
yeah these are in this picture you can
Right,
see
thank you.
that is just at the configuration at low pressure. These are at high.
I agree.
Yeah.
Short question. So you can just go to the next slide. Yeah, this you say this is spherical. Yeah, this spherical look like ellipse. No?
What?
So go to the next slide. The snapshot.
Previous one.
Yeah, the previous one. Yeah, this one.
Yeah.
The middle one, right?
Yeah.
You said this is spherical.
No, this is this 2D pair collision, GXX or GXY. This is not. This just points out that there is this 2D hexagonal order. 2D hexagonal order.
The strength is lying around the center and then it is
Yeah.
a smaller.
Yeah.
Okay. Fine. Let's thank Rahul then.
Thank you.
Wasting time. Vishnu, you are next. So Sheikh is going to talk about some work that we have been doing on generalized RNA-seq.
Okay. So, good morning all. I am Viswajit Kumar, a PhD student here at the Institute of Mathematical Sciences. Today I will be talking about the generalized Arrhenius law and how one can use this generalized Arrhenius law to extract some properties of unknown energy landscapes. So, this talk is taken from works done with my supervisor Arnab Pal and collaborator Ohad Spielberg. Let us consider a potential landscape which has some metastable states in it, and the central question of the talk is, can we quantify the metastable states in an unknown energy landscape? So, specifically by that I mean, can we count the number of metastable states in an unknown energy landscape? As we go along, we will see that the traditional single particle Arrhenius law won't be able to say anything about metastable states in a landscape. However, the generalized Arrhenius law will be able to count the number of metastable states in an unknown energy landscape. Therefore, this talk is divided into three parts. In the first part, I will talk about traditional Arrhenius law. In the second part, discusses generalized Arrhenius law in interacting diffusive systems, and finally, how we can use this generalized Arrhenius law to infer the number of metastable states in an unknown energy landscape. So, let us start with traditional Arrhenius law. So, after analyzing several chemical reactions data, Arrhenius came up with his empirical formula governing the rate of chemical reaction, which is given here. A chemical reaction is often realized as reactants overcoming some activation energy barrier to form product. After several years of the discovery of Arrhenius law, Kramers came up with his diffusion model of chemical reaction, where he considers a Brownian particle which is diffusing in a potential landscape, and it is trying to overcome a barrier of height delta U to go to other side of the barrier. So, he showed that in the limit when the height of the barrier is much greater than the thermal energy available to the particle, the escape rate is given by this simple formula. If you the resemblance between these two formula at once establishes the diffusion model of chemical reaction given by Kramers. Only you have to identify the height of the barrier here with the activation energy barrier in case of chemical reaction. Because of this similarity, I will henceforth use the term Arrhenius law and Kramers escape rate formula interchangeably in this talk. Okay, so let us go a little bit deeper into this Kramers escape rate formula. So, you see that escape rate depends only on the height of the barrier. So, experimentally, if one can get the data for escape rate of particle at different temperature, one can infer the barrier height in front of the Brownian particle. However, this Kramers setup cannot count the number of metastable states in a potential landscape. With this message, let me introduce generalized Arrhenius law for interacting diffusive system. So, what kind of system we are talking about? So, the system is diffusive. By that I mean the system needs to obey Fick's law, and one example of the system that we took to understand generalized Arrhenius law is simple exclusion process, where a single site can be occupied by at most one particle, and a particle can hop to its nearest neighbor given the target site is empty, otherwise it will stay put. So, hence there is a excluded volume interaction in such a system. The other example of the system that we took is of zero range process, where now any number of particles can sit on a single site, and rate of jump of the particle from a given site depends on number of particles on that site. And this is the setup that we used for generalized Arrhenius law. Basically, we have a lattice system of size capital L, and we invoke a reflecting boundary at the initial site and put a absorbing boundary at the last site, and we put everything in a external potential. We take finally the system size to be large, and also since our system is diffusive, one can do diffusive rescaling, and the whole system, this whole system with external potential will look like this, where now I have a reflecting boundary at x equal to 0 and an absorbing boundary at x equal to 1. And what is the question that the setup asks? We ask the question that what is the escape rate of the fastest particle. By that I mean what is the rate of absorption of the first particle that gets absorbed at x equal to 1. So to answer this question, we used macroscopic fluctuation theory to derive the generalized Arrhenius law form. However, I am skipping all the technical details because of the lack of time, and here is the result, that the escape rate is given by this simple formula, where this symbol implies this relation, and rho 0 bar is nothing but the density of the system. Notice that there is an extra term present here in the escape rate formula, which was not there in case of single particle. So as a teaser, this term will be responsible for counting the number of metastable state in a potential landscape, in an unknown potential landscape. But before going there, let me talk more on generalized Arrhenius law. I already said that we used macroscopic fluctuation theory to get to the result of the generalized Arrhenius law. However, there is an intuitive way to understand the result, and the intuitive way corresponds to preparing the system in minimum energy configuration. So let us consider a potential landscape which has its minima at x equal to 0, and it increases monotonically, let us say. So for this simple exclusion process, where at most one particle can sit on one side, the minimum energy configuration would correspond to particle start stacking up near x equal to 0 as close as they can, as close as allowed by the underlying dynamics of the simple exclusion process. And this, the topmost particle fills a potential u top in minimum energy configuration. Hence, in this configuration, this particle does not see a barrier height delta u, rather it sees a barrier delta u minus u top, and we say that this delta u minus u top is nothing but delta u times g, and here is the result for simple exclusion process. For zero range process, since any number of particles can sit on a single site, we say the minimum energy configuration is all the particles sitting exactly at x equal to 0, and that means u top, the topmost particle, fills potential exactly equal to 0. We take the potential at x equal to 0 to be 0, so this is exactly equal to 0, and this relation then implies that g is identically equal to 1 for zero range process. Okay, so let me reiterate the result again. So for zero range process, what we got is g is equal to 1, and for simple exclusion process, we have different g, form of different g for different kind of potential that we took. For example, for linear potential, the g is given by this formula. However, for harmonic potential, it is given by this formula. So we see that this g, function g, depends on the form of potential landscape we choose, and therefore we already have a hunch that this g can give some information about the unknown landscape if we choose some unknown landscape. With this, let me talk about how do we use this generalized Arrhenius law to count the number of metastable states. So let us consider an example where the potential is a piecewise linear potential u p w l of x, and here is the function g plotted. This g function is determined from minimum energy configuration argument, and we can see that there are two kinks in the function g, and also notice that there are two extremal points of the potential, one here and one here, the maxima and the minima, and there are as many kinks as the number of extremal points in the potential. What it means is, if I can count the number of kinks in G, I know the number of extremal points in the potential landscape, and divided by 2 will give me the number of metastable states in the potential landscape. So this is the message from this slide, that if we know the kinks in G, we know the number of metastable states in the potential landscape. okay. So, but there is a problem that this function g, as I said, as I showed here, just a second, this g is obtainable only in beta delta u tends to infinity limit. Yeah. So, g is obtainable only in beta delta u tends to infinity limit, which is not feasible experimentally. So, what we can do? So, the solution of this inapplicability is drawing a correspondence with thermodynamic phase transition. So, a thermodynamic phase transition usually thermodynamic phase transition point usually corresponds to a non-analytic point in thermodynamic potential. However, the non-analyticity is not apparent in finite size limit, it is only apparent in thermodynamic limit. Let us come back to our problem. The non-analyticity in G, which is the King's, the non-analyticity in G is apparent only in beta delta u tends to infinity limit. Hence, we say that beta delta u tends to infinity limit in our system is nothing but the thermodynamic limit of the phase transition, and similarly the density here corresponds to temperature of the thermodynamic phase transition. Having drawn this correspondence, we can now define the free energy of the system, which is given by this expression, and it is important to notice that free energy in the limit of beta delta u tends to infinity is nothing but this function g, and that similarly response function is defined as derivative of this free energy f with respect to the density of the system. So, to show how this introduction of response function helps us count the number of Kings in G even at finite beta delta u, let us consider an example where the potential landscape has 2 local minima and 2 local maxima. So, there are 4 extremal points, and therefore, there are 4 Kings in the G function G. This function G is again determined from the minimum energy configuration argument. Let us see the right side of the right side figure. We have the same potential plotted, but 1 minus of that potential is plotted, 1 minus that potential is plotted in the function G, and we see that as we increase beta delta u, the function f, the free energy, converges more and more onto the function G, as it should be, because function G is nothing but free energy function in infinite beta delta u limit. In the next, we plot in this to plot the response functions R2 and R3, the rescale response functions, and this vertical dashed red lines are the actual position of Kings. Again, the actual position of Kings are determined from minimum energy configuration argument, and we see that as we increase the beta delta u value, the peaks of the response function get shifted towards the actual position of the Kings. Thus, we have counted the number of Kings in G through the response functions even at finite beta delta u. With this, I conclude that traditional Arrhenius law can infer the barrier height, but it cannot infer anything about the metastable states. However, generalized Arrhenius law can count the number of metastable states through the response function. Thank you.
Questions? Ajit?
So I have a couple of questions. So where is it useful to know the number of metastable states? Second, does this result apply only in one dimension or external?
This so first question. So this when you know the metastability in a system, let's say, you can kill out some fast degrees of freedom, simplify the system.
But you only know the number, right? You don't know what the state is.
You don't know the location.
Yeah.
That we cannot infer.
Yeah, the location is not inferred here. We know the number.
And we had a second
Yeah, the second question.
Dimensionality.
So we think this is easily extendable to all the dimensions. We need to check.
But then interaction is very expressive.
Yeah, this interaction is specific in the sense we used macroscopic fluctuation theory, so that is applicable for diffuse system. Okay. Yeah.
I have a comment with the question. Right? The comment is on the previous question. Even getting the number of metastable states is extremely valuable because that gives you the entropy of the system. The number of metastable states that gives a measure of how much the system is in non-equilibrium, right? Away from the equilibrium. It gives an order parameter for the degree of the non-equilibrium nature. That's why I would implement it. Get the comment.
Can you just elaborate a bit more on this because it's not getting me what.
When you have the many metastable states you are creating, a particular system when it creates, there's a protection of the entropy. Right? Because these are not an exotic system. That's the reason we have metastability. So therefore you have a measure of how much away you are from the equilibrium state. Yeah, so you don't really. It would be nice to know the locations, but it's still the enumeration of the number of metastable states is a measure.
So one of the most
That's definitely, that's for sure. Yeah. Then there are lots of examples that we saw, but we didn't get in this way. I mean, this kind of direction we didn't have. We didn't know that it can be measured for non-equilibrium.
This question I have. So I have a stupid question. You are saying unknown energy landscape. Please explain what is the meaning of unknown energy landscape. Any physics problem, the potentials are given.
Yes.
So I know some landscape. I cannot quantify the structure just as saying how many metastable states you have, how much global minimum local, and we don't know. But in that, what is the meaning of unknown?
So let's say a particle is moving across some surrounding which
you were saying.
Yeah.
I don't remember your sentence, but I was saying that counting the metastable state.
Yes.
It's a difficult problem. And you are pursuing that. Then you are saying you are somehow trying to find the energy landscape. Means it looks like you don't know even the potential energy. That is
you don't know the potential landscape a priori, and then you count the number of
through the
metastable.
counting of this metastable state, can I guess a potential energy of the system?
No, you are just counting. No, you are just counting the number of metastable states in the system.
You
cannot construct the potential landscape.
No,
you will have some knowledge about the potential
real
landscape.
system you don't know the potential.
Yeah.
You guess. You always model, right?
Right.
But the way he has started, it looks like a very promising big thing. You are metastable counting a state, and you are actually probing unknown energy landscape. Means somehow you are guessing the potential.
Okay, so maybe it was slightly like in the phrasing of his thing, but the idea is essentially that it's just the counting number of metastable states and not constructing the landscape at all. I mean, that you cannot do it.
Yes.
So my other question is probably a very basic question. If you go to the definition of G rho naught, you had one slide, logarithm of R. Yes, it's right. So this is kind of very surprising to me, right? When you do the extra term, I take that term and put it in there, and you have an identity, R is equal to R. Right? You have logarithm over R, and that constitutes an argument of your exponential, you're getting it right. So e to the log R will give me an R. So I don't quite understand what's going on. Do you see my question? This rho R,
This
you have
one?
written as the logarithm of R,
Yeah.
and I substitute the logarithm of R there.
So okay, so this is
Sorry.
this is the meaning of this asymptotic sign. This result is true in large beta delta u values with some correction.
Yes, but then you get R is a constant, right? You get it right? 1 over beta delta u log of R. You just cos beta delta u, you have, right? Put minus log R is, right? And then take exponential of this. I'm just asking a very, very basic question. So maybe it's right.
No, from there to there is identity. The next step you are talking about this limit is not needed.
Yeah, that's what
You need this essentially to extract the G of
That's what I don't understand. So that the definition of your G or not that is it's odd, the definition of odd, because you are getting the rush, right?
You should start from there. Minus beta delta u should be greater.
Relation you have for G, I think, is the previous one in terms of this activation. Delta U.
But not this one.
Not in the sense like here, okay, so it has a
No, go to back. He has, I don't know.
He has a
Go
different one.
back.
The real one, which is essentially that he says this is the one. This is the correct one.
The on the back is defining that. No, go back.
I will tell you why that. I don't know why there's.
No, he describes the RNS, where KBQ is much less
Yeah,
than KBQ.
that is the limit.
False when U is much less than KBQ, right? Greater than you, that equation.
Yeah, that is the limit
Second
basically.
I will explain what is the connection of this one.
No, that equation I know you retain that this will hold when beta delta U much less than something. In the second selection.
Yes.
You go and you show the.
Maybe if not any further questions, we'll stop here and then let's end. The last one before the coffee break is viral.
Do you think it takes you want to like all of it or not? No.
It is just consistent. It is being So, I will talk to you and we'll talk about some past passage. Stop exactly.
Take your time, it's so interesting.
Explain everything, very interesting.
Yeah, so hi, I am Aurup Biswas. I am a PhD student at this institute. So I mostly work in the field of fast passage processes and strategies to expedite a fast passage process. So some of you may already know what a fast passage process is all about, but still let me give you a brief intro. Suppose there is a searcher. It starts from x is equal to 0 at time t is equal to 0, and the job of the searcher is to locate the box placed at x is equal to L, and we are interested in the time it takes for the searcher to start from here and locate the target at x is equal to L. So such kind of processes which completes after a certain amount of time is termed as fast passage process. It's very simple, but still we are mostly interested in how long it takes for the searcher to reach here, what will be the best strategy to find the target or the box, like that. For example, take the searcher is moving with a constant velocity and it is following a straight line path starting from here to here. Then the time it will take for the searcher to reach the box is simply L by V. That means this time capital T is termed as the fast passage time, and in this case the fast passage time is L by V. However, in most of the physical processes, things are not that much simple, and many cases the searchers follow the stochastic dynamics to reach the target. So that means if in one realization the searcher can follow a stochastic path like that, and it can consume a time say 3 seconds. But if you run the simulation again, it can follow another stochastic curve and it can take another random time, maybe 5 seconds. In those cases, one generally asks what is the mean or the variance or the distribution of this time capital T, because it's not a fixed quantity, it's a random variable, and one is generally interested in the distribution. That's what we shall be mostly interested in my talk. Before that, let me just give you why these fast passage processes are interesting at all. So in many physics problems, like even in the few talks earlier, one is generally interested in the finding some desired location in the potential landscape. So the desired location can be a global minima, global maxima, or any other place in the landscape. And while doing the simulation, one generally takes the approach where one starts searching parallelly, starting from some position, and search for the desired location. And whenever one of the run finds a location, you stop the process and note the corresponding time. For example, here this green trajectory goes towards the desired location, which is like lighting up, and you note the corresponding time. In a more biological problem, one encounters when a protein searches for the target site in a DNA strand. So the protein slides across the DNA strand in a stochastic fashion, and whenever it finds the target at target site M, we mark the process as complete and note the corresponding time. Another one is this polymer translocation problem. So there are two components. One is this polymer and one is this membrane with an opening. So the polymer does its own random stochastic dynamics, and by following the stochastic dynamics, the polymer can pass through this opening and reach to the other side of the opening. So one can ask how long it takes for the polymer by moving randomly to pass through this opening and reach the another side of the membrane. So this is again a fast passage problem which completes after the polymer goes this side. And apart from this physical or biological example, there are another man-made artifacts such as stock market, where, for example, one often asks when a stock will cross a particular threshold. So when the stock price goes very high, they will immediately sell their stocks, and in that case also one can ask, starting from here, how long it takes for the stock price to cross a threshold. And this is again a fast passage, and one is interested in the distribution of this time, which are usually random. So these are some typical intro and the example of fast passage processes. But what is the problem? So the problem is having these heavy tails in the fast passage time distribution. For example, take this searcher problem, searching for this box. So if the searcher is going to the target or the box in a finite time, there is no problem. But even now, suppose the searcher is moving in a stochastic fashion, then it will follow some stochastic trajectory, as I told earlier, and it will take some time, capital T. However, those trajectories which will go in a completely opposite direction from where the box should be will give rise to an infinite value of this fast passage time. Because the searcher is moving stochastically, it does not know a priori where the box is, and it may never find the box. And this overall gives rise to a heavy tail or the power tails in the distribution, which implies that all the moments of this distribution, that means the mean, variance, everything is infinite. That means simply if one asks how long it takes for the searcher to start from here and reach here, it is infinite. So the search will never complete. The fast passage process will never complete. So that is obviously do not want. We want the fast passage process to complete in a finite time span. And that is the question. How can we improve our fast passage process? So there has been several strategies that have been found by people from like years and centuries, but we are working in the kind of the dynamics or the strategy which is known as intermittent switching dynamics. So let me first elaborate what is it all about. Take the same search problem. Now the searcher moves in a stochastic fashion, not in a deterministic fashion. Starts from here, moves in a random fashion, and starts and locates the target here. These trajectories are very good. It is finding the target in a finite time, no problem. However, what we impose is that suppose the target searcher starts, like in our switching dynamics, suppose the searcher starts from here, it starts moving randomly and it searches for the target up to a time r. If that searcher does not find the target up to this time r, it decides not to search anymore and returns towards the starting position again, following some another stochastic dynamics that we can impose. So in this switching dynamics, there are two phases. One is the search phase and one is this return phase. In the search phase, the searcher is performing its own underlying dynamics to locate the target. However, in the return phase, the searcher's main job is to return towards the starting position or its home. And after it returns to its starting position, it renews the whole search process and starts searching again for the target. So this is the simple strategy with search and return phase. And what we found is when we impose such kind of return dynamics on the searcher's motion, then you see that distribution is rendered from power law to an exponential tail. So in the underlying search process, we saw there are several trajectories which are going opposite towards the target, which was giving rise to this heavy tail in the distribution. However, when you impose this return dynamics on the searcher's motion, the first passage time distribution becomes exponential tails, and that in principle implies all the moments of this distribution are finite now. So earlier you had distribution or the process with infinite mean, variance, everything, but now you have, with this new dynamics, you have all the moments finite. So the physical reason for such improvement is like this. So these are the underlying search process. However, the heavy tails were coming from the trajectories which are going completely opposite direction to the target. Now by imposing this return dynamics shown by this red dashed line, we do not allow the searcher to explore regimes which is not beneficial for the search. For example, here the target is here, but now the searcher is going in opposite direction. So we cut off these trajectories and tell the searcher to restart its search process back from the original position again. So by cutting off these tails, we make the process we improve the process, and we get this exponential tail. So we also have a theoretical framework for this process. It is very simple. So suppose TR denotes the overall random variable associated with the overall search time. Starting from here to here, it takes TR amount of time. Now TR has two contributions. One is from this underlying process capital T, like it is just going to the target and finding it without any return events. And the second one is with one return event. Suppose it is searching and then at time stochastic time R, it decides to return. Then this time R is added, and also this time tau of x. It is the time needed for the searcher to start from here and reach here, and this is also added. However, after returning here, the searcher restarts its whole search process again, and this TR comes here, but it is an IID variable of this TR, independent and identical copy of this TR. So this is the renewal structure, and starting from this renewal structure, you can find all the moments and even the distribution of the search process under this new return mechanism. And here I show the exact expression for the mean, where each of the terms you can find explicitly given any kind of first passage process. So here one term contributes to the search process, and another term contributes to the return process. And using this expression, you can ask, is that so that this switching dynamics will help you in any kind of first passage process? The answer is simply no, but you can derive a criteria when this new switching dynamics will indeed help you to expedite your first passage process. So you can simply use this criteria, like TR is the mean first passage time of your first passage process with this return dynamics, and this T is without the return dynamics. And with this, you can simply show that when the CV, which is the ratio of the fluctuation to the mean of the underlying process's first passage time distribution, that means by underlying process I mean without any return events, and when the CV is greater than 1, that means fluctuation is greater than the mean, then you can clearly use the new strategy and expedite your process. So CV essentially quantifies the broadness of any distribution. For example, in this case, when CV is very small, the distribution is very sharply peaked. For the delta function, the CV is exactly 0 because it is just a single peak. However, when CV is very high, it is greater than 1 or infinity, in that case the distribution is very broadly peaked. That means the fluctuation is very high in those cases compared to the mean, and those are the cases where the new strategy of return dynamics imposed on the first passage process will indeed help you to minimize your mean first passage time of the process. And this is all what I wanted to tell, and this is the summary. Like this is the return process, and like you get this exponential trend from this heavy law tail, and the criteria that it must satisfy just depends on the first two moments of the underlying process of first passage time distribution. If you know the mean and the variance of the underlying processes first passage time distribution or the first passage time, then you can without doing anything, you can clearly say if the new strategy will help you to expedite your first pass time or not. Thank you.
So thank you, Madhu. So questions? Comments?
So what does the coefficient of t depend on?
Oh, it's like I just make dv to a dimensionless quantity, but it's not.
Yeah.
For example, okay, for
the r, does it depend upon r?
R, yeah, R means L.
No, on that side.
So there must be some, if r
Return time.
Return
No,
time.
return time. After what time you want to
Okay, I see.
If that is small, then you will still have this algebraic decay.
Okay, so let me just go. Okay, let me just. Yeah, you are talking about this R, right?
Right. That time. If that time is short, then the distribution will be exactly.
Absolutely,
So
yes.
there must be some critical value of R
Absolutely, yes.
when you are going to have this benefit.
Right.
So what is that?
Yeah. So yes. Now this R is stochastic time, and you are absolutely right. If it is very small, then again it will be a heavy tail. So then you need to consider specific distribution. For example, if, like these all on a formalism level. Now, what are the exact problems that you want to find? For example, take the simple diffusive search problem. There is a diffusion, and like a particle is diffusing and want to find this target. Then you can clearly show, like if you solve the problem, this R can be optimized. If you take R to be very zero, it will not help you. But again, if you take R to be very high, it also help you. But the good thing is everything you can show in this CV criteria. So this CV criteria will tell you what will be the optimal value of R that you have to find. So I have not shown any exact example here, but given any example, you can clearly this R will be dictated by the CV criteria.
Okay, so along the same token, right? If you go to the transition from algebraic decay versus the exponential decay, it's the effect also.
Right.
And what is that?
Yeah. So yeah, then that again depends on the transition. So for example, if you take a simple diffusive search problem. So diffusive search problems mean first passage time is itself infinity in any dimension. But yeah, if you take a deep diffusive system or any system, even any system where the mean first passage time is finite, then you can clearly show what kind of transition it goes through. For the simple, and it also again depends on the systems under consideration. For the simple deep diffusive system, it's the first order transition, second order transition. But it like the kind of transition depends on the specific dynamics considered.
Right. So therefore, the transition from the algebraic decay to the exponential decay could exhibit a phase transition.
Right. Yeah.
Dynamical phase.
Absolutely. And that has been already quantified in this theory. That has been done. Yeah.
See, this is very interesting, but when you are describing this search, are you assuming a flat space?
No,
You
the
are
search.
assuming a flat space or
No, the search can be even under a potential also.
I'm not talking about. Listen, do you understand flat space?
I mean, without potential. I'm not sure.
Do you understand Euclidean space?
What?
Euclidean space?
You mean X,
What,
Y, Z?
where are you searching?
The search can be in position, like
This is the space you are searching, huh?
yeah.
So this is a, what you call a flat Euclidean space or something else?
I'm not familiar with this flat Euclidean space, but what I
So if you are not familiar, I cannot answer.
okay.
What was the question regarding?
No. If you are in this search there is a metric involved, right? This is a system is embedded in a 3 dimension. That 3 dimension is Euclidean space. So person is walking this direction. In your simulations, I don't know what you are doing, how you are
So
computing.
at least for the diffusive cases, etc., like that's happening in real space.
But
there are also configuration spaces.
No, configuration space is different. In the real space itself, if I change the space only, it is like a Riemannian space or something like this. So what will happen?
Yeah. So more questions, more comments? Not.
Okay, one thing that I asked, this problem is what he is doing. It looks like walking from one point to another point in space. So it is just to minimize the variational calculus. It will minimize that all the things. The action, if you minimize, the time will be extremized. But in the Lagrangian formulation, you solve the problem and you get everything. Why is he doing this? Why not just minimize the Lagrangian. Certain distance is
That doesn't, that will not necessarily minimize the mean time, no?
No. This is everything is there. You don't need to minimize anything. Like if you minimize the action, then your path is an optimized path. Right? But the problem I understand here, in that whole problem, you don't ask the distribution of time. Where you are asking this, whether you are getting how to collect which time, all those things. But why are you doing this stochastic? Everything is ready. Lagrangian formulation, what problem is it?
No. I think that the point so the point that they are making is when you look at the first passage of time, as he pointed out, in the average first passage of time, there is actually a distribution of first passage of time. You could calculate for a particular stochastic process, you can calculate that distribution. That's how you get the mean distribution. You could minimize that. And that answer will be different from the answer they have here, because they have superposed additional dynamics on top of the intrinsic dynamics.
Right, yeah.
That's what they have.
There is a...
That's the reason why they are able to excite a dynamical phase transition. Because there are two possibilities going on.
Yeah, because of the switching, but regardless, the original first passage problem, forget about the intermittent dynamics, etc. Therefore, the original process, people have tried to use something called Feynman cat, which is basically some sort of path integral formulation to get this. But it's just it's quite cumbersome and lengthy process, and you cannot go beyond diffuse process mostly. So there is no point. So there's a whole methodology essentially is to bypass all the things and do something else. Although you had a question?
Yeah, is there any restriction on the tau x, the return time distribution?
There is no restriction, but it's like generally you can take it to be 0 also. It's return time, but it can be anything.
I'm saying if the return time is also long, then will it get...
Yeah, then this CV will change. Like then it like okay, so the CV I have shown here is for r is equal to 0, but yeah, for if you have
Tau is 0.
sorry, tau is equal to 0. Sorry, for tau is equal to 0. If you have tau, then this tau will also come in this CV also.
So the CV is for the underlying process. This CV we are
Right,
calculating
underlying
for
process.
the without resetting process.
Right. It is written.
If there are no more questions, so we'll just end this session and also let's thank the speakers for taking time. So I think the original coffee break was for 15 minutes or so. But let's give it to 10 minutes. So we'll meet at 12:40. Yeah?